In this video, we're going to be looking at topic 1H, which is metallic bonding. And metallic bonding is a triple-only topic, and it is part of the IGCSE course from Edexcel. So the learning outcomes in this topic are to look at how to represent a metallic lattice using a 2D diagram. This is a common exam question asking you to draw it out. How we can understand metallic bonding in terms of electrostatic attractions. And remember, this is the key term used in all of bonding. We're always looking at how they are held together using these attractions, and then being able to explain the physical properties of metals based on their structure. So in a metal, the outer electrons tend to be the furthest away from the nucleus, and for some metals that can actually be very, very far from the nucleus. And this distance causes them to be very weakly held, meaning there is less attraction to the nucleus. Now, the effect that has is when a number of metal atoms, all from the same element, get close together, such as when we have a solid or a liquid, the outer electrons are far enough away from the nucleus that they actually become free to move because they have different attractions for other atoms within the substance. So what actually happens is the outer electrons move from atom to atom. And when the outer electrons are left and they've moved to another atom, that's going to form a positive metal ion or a cation. So those cations that have lost those outer electrons all stay in place, and they are then surrounded by the sea of free electrons or delocalized. And delocalized simply means free to move, meaning the electrons delocalize from the atom and they move around all of the atoms within the metal, and they are then attracted to the cation. So we get this electrostatic attraction between the negative delocalized electrons and the positive cations, and it's this electrostatic attraction that holds all of the metal atoms together, and we call this metallic bonding. We can show this in a 2D diagram like you see here. So we have our lattice of metal ions, and remember, a lattice simply means that it is a regular arrangement of positive ions. So we have our rows and our columns of ions, so you'll have seen a lattice in ionic bonding. And then these ions are surrounded by a sea of delocalized electrons. Now notice that the electrons in the diagram are drawn very small, and the cations have a positive sign and they are bigger than the electrons. This is quite important when you're drawing your diagram. You want to try and be as accurate as possible. And as we said, metallic bonding is defined as the electrostatic force of attraction between the positive ions and the delocalized electrons. So this is a key definition that we have to know. Now, within a metallic structure, there are no individual molecules. All of the positive ions in the lattice attract all of the delocalized electrons. So unlike a covalent structure where you have these discrete individual molecules, a metallic structure, there is an attraction between all the positives and all the negatives, and it's the overall attraction that holds everything together. Now, the number of delocalized electrons will always balance out the number of positive charges. So the overall metal is always neutral. So if you have a group 1 element that is going to form a 1 positive ion, each of those atoms is going to lose 1 electron. So if you have 16 positive ions, all with a 1 positive charge, that means you're going to have 16 delocalized electrons, because each one of them has lost 1 electron. If it was 16 2 positive ions, then we would have 32 delocalized electrons. So we're always going to balance out those charges because the overall metal is neutral. And the ion formed will still depend on the number of electrons in the outer shell. That doesn't change from when you learned it in ionic. So group 1 make 1 plus, group 2 make 2 plus, and group 3 make 3 plus. Don't worry about the transition metals. You are not expected to know exactly what charge they make because that's A-level work. You would be told for a transition metal what the charge is. So you would be told something like copper 2 or zinc 2, silver 1. And you've seen that in topic 1E when you've looked at formula and calculations. All metals are going to have very similar properties and they will all share the following list of properties. Some, however, will be better than others. So all metals are all good conductors of electricity, but some will conduct electricity much more than others. You don't need to give specific examples, you just need to be aware that there is a level of difference with these properties. So they are conductors. They all have high melting and boiling points, with the one exception of mercury, because we know that that is a liquid at room temperature, one of only 2 liquids on the periodic table, the other being bromine. They are also good conductors of heat, so we have heat and electricity conduction. They are very strong and they are quite dense, meaning we have lots of particles in a small volume. They are malleable, and malleable just means that they can be shaped. So we can change the shape of a metal, and you actually know that just from common sense. If you look at all of the different car shapes that you can get, we know that each of them has been constructed out of an iron or a steel frame, and every single car model looks different. So we've been able to shape the metal into those different structures. We also say that they are ductile, meaning they can be drawn out thin into wires. And again, some metals are better than others for this. Copper is a particularly ductile metal, and because it is a very good conductor of electricity, we actually use copper in a lot of our electrical wiring. And all of the metals are going to be solid at room temperature, again, with the one exception of mercury, which is a liquid. Now we're going to focus on a number of different properties and being able to explain them by discussing the structure of metals that we have just looked at. So the first property is melting point. Now the strength of the bond, or the metallic bond, is going to depend on how many outer electrons have been lost and how many have been delocalized, and then the strength that the nucleus has to attract these and the strength that the cation has. So what we tend to find in general is that the higher the charge on the ion, that gives you the more delocalized electrons. We're going to get higher attractions, therefore we get stronger bonding. Okay, the more positive and negatives we have, the more they are going to be attracted to each other. So if I have, for example, 10 positives and 10 negatives, they are going to be much less attracted than 20 positives and 20 negatives, which in turn would be less than 30 positives and 30 negatives, and so on and so on. So the more positives and negatives we have, so the more delocalized electrons and the more cations, the stronger the attraction, therefore the stronger the bonding. And in order to overcome those strong bonds, we need to put in a high amount of energy. And this high energy, to break the bond, so we need a high energy to break the bonds or overcome the attraction. You can phrase it in both ways. This is going to then give us this variation in melting points, but in general, because they are high energy, we are going to have high melting points. But the strength can vary because we can have group 1 versus group 3. So group 3 is going to have more charge or more delocalized electrons in comparison to group 1. So you probably see that aluminium is going to have a higher melting point than something in group 1. We can also look at the conductivity. So conductivity is defined as the movement of charged particles. And in this case, the charged particles that we're looking at are delocalized electrons. So these delocalized electrons are able to move throughout the structure, and they are then able to carry a charge. And the delocalized electrons being able to carry the charge and to move allows the metal to conduct electricity. So what we can see in this diagram here is that if we put the positive terminal of a battery or a cell into, or some sort of power source, onto a metal, all of the electrons are going to be attracted towards that power source because the negative electrons are going to be attracted to the positive. So you're going to see this movement of charge here, so they're allowing the electrons to flow along the wire. On the other side, we have the negative terminal of the power source, and because negatives and negatives are going to repel each other, that is going to also push the electrons away from the negative terminal. So not only are we getting the pull from the positive, we're getting the push from the negative. And this movement, due to the attraction or repulsion for the positive and negative terminals, allows this conduction of electricity. As we've mentioned, we can hammer metals into different shapes, or we can draw them out into wires, and we call this malleable and ductile. And the reason that this happens is we've got layers of our positive ions all in our diagram that we've seen, and when we apply a force to one of the pieces of metals, or to a piece of metal, the layers of positive ions are able to slide over each other. So because they are able to slide over each other, it allows them to move and allows them to change shape. However, it does not affect the bonding. So it doesn't break up the metal, it just simply shifts the layers so that they move past one another. And this being able to move past one another allows us to change the overall shape, and we call this malleable and ductile. So let's finish off by looking at a past paper question. This reaction is telling us about nickel, and nickel has a melting point of 1455, and nickel is a good conductor of electricity. Now, what you will find as you go through this course is you will learn a little bit more about nickel, and this is actually part B of a question, and part A likely would have told you that nickel would make 2 positive ions. And what we want to have is we want to show a label diagram to show the arrangement of the particles in nickel. So we want to have our diagram showing at least 2 or 3 rows and at least 2 or 3 columns. I would say in general, you want to draw out at least a 4x4 diagram, just so that you can clearly see that you're covering all of your bases. So you're going to draw your circles regularly arranged, and these are going to become my cations. You can see I'm trying to evenly space them all out and make sure that they're staying in a row. Now, because of this particular question, they're not really specifying in particular about the charge. You can just write positive, or you can write 2 positive. They will accept both answers in the mark scheme. So you've got your circles with your positives, and of course we always want to have a labelled diagram. So we're going to label this as positive ions, or we could even call them cations. Please note that you have to specify that they are positive ions. If you just write ions, you'll not get the mark. And then we have to show that we've got some sort of electrons in between. So I'm just going to write them out as E. And I should have all of my electrons being spaced out all the way through. Okay, they don't have to be perfect, but then we can also just show that E are your delocalized electrons. And showing that that's what that means. So there we've got our labeled diagram. So you want to have it labeled or some sort of key to show that we're going to have delocalized electrons. And then for 4 marks, explain in terms of its structure why nickel is malleable and why it is a good conductor of electricity. So we've got 4 marks, 2 separate parts of the question, so we're going to get 2 marks for each. So if we start off with why it is malleable, this is because we have layers of cations are able to slide over one another or slide over each other when a force is applied. So the key information that we should be saying here, the key words are looking at layers of cations and sliding over each other. Please make sure that you use the word cations and you don't use the word molecules. They will accept atoms, but ideally we should be referring to them as cations. And then the second part is looking at conductivity. And we have conductivity because we have delocalized electrons that can flow when a potential difference or a voltage is applied. So that's when we've got our positive and negative terminals. So we don't need to draw any diagrams here, we can just simply discuss the actual terms. So again, for conductivity, we're looking for delocalized electrons and talking about how they can move or they can flow. Please don't use the word free. They will not accept free electrons. You should always be using the term delocalized. And there you've got the mark scheme for these questions. Now that's everything for topic 1H, metallic bonding. There are lots of questions on this from previous past papers. You might want to check both the old double and triple because they were in both. And there are lots of questions on this topic in the textbook as well. So if you're not sure about anything, you might want to give them a try. If you have any questions, please feel free to leave a comment below, and I hope to see you back on the channel soon.